Hi, Joseph from Ventitech Solar here. Today we're going to talk about energy storage systems. It's a topic that is coming up more and more often because the prices are coming down on batteries. So let's take a quick introduction. We're going to have another video for more detailed comparison, but what other names do we have for storage systems? It used to be solar batteries, only because they were coupled with the solar PV array. Now the new name that we're using a lot is Powerwall, and it's basically a product from Tesla that is becoming more and more popular, so everybody think about Powerwalls as home storage system. They can also be called whole home batteries, home energy storage, and lastly energy storage systems, which is the industry standard for this battery system. As far as classification, there are basically two ways to classify the batteries: AC coupled, DC coupled, and also by the chemistry that is used. AC coupled is when alternating current is used between the battery system, the storage system, and the rest of the home or the solar PV array. And direct current is the system used for connecting the solar PV to the batteries. Home batteries by chemistry, the most popular today is lithium, nickel, manganese, cobalt oxide. It's also shortened by NMC, nickel, manganese, cobalt. There's also nickel, cobalt, aluminum, and it's NCA, which is less popular, it's more expensive, and it has probably more power output short term. And the latest coming up on home batteries is lithium iron phosphate, abbreviated as LFP. We'll see the characteristics of each one in a minute. And the non-lithium batteries, which are the lead acid, the same 12-volt battery that your car uses. It's the technology for probably 100 years or so. Now, AC or DC coupling, pros and cons of each. And on the DC side, it's the most efficient way to connect the batteries to the solar, given that both of them work on DC energy, DC power. There is also less components in between the storage and the solar, so less components to go bad or break down. On the cons, we can see that it requires compatible inverter. So basically the battery and the inverter have to be very well integrated to be able for the inverter to control the batteries and know exactly the state of charge and how to charge them, etc. Another con is not easily retrofitted to existing solar PV panels. So if you have already a solar PV, it will take significant integration to add a battery system. There is also DC coupled battery systems are typically installed with the solar PV because of the same difficult to retrofit. Now on the AC side, there are some pros, like compatible with most solar inverters, easy to retrofit to existing solar system. Both of those are combined or can be into one. The location for the storage system is more flexible. It doesn't have to be right next to the batteries, and you don't have to run very thick cables between the batteries and the solar system. Cons, well, it's less efficient, and less efficient because there is more energy conversion or power conversion from DC to AC back to DC. And when you're going to use the power, then you have to do the reverse from DC to AC. So, and every conversion there is power loss. So they're less efficient. Even though they're more flexible, they're less efficient as far as energy. Cons, also this kind of system include more electronic components. So there is the inverter for the solar system, there is an inverter on the backup batteries, and there is rectifiers and a bunch of other power converter, DC to DC converters, etc. So more things to go around. Let's look at the efficiency in more detail, the efficiency of DC compared to AC systems. And here in the top left we have a solar array, then we have an inverter, charge controller, backup DC coupled battery in the bottom left, and then of course the inverter connects to the AC wiring for the home, and in here we have one home appliance on the top. So let's suppose that the solar array is producing 100 watt-hours fed into the inverter. At the time that is converted, because it's only DC to DC, so it's only changing high voltage to low voltage, minimum 2% power loss in there, energy loss. So 98 watts hour. Now, when the power is going to be used, this 98 watt hour needs to come out of the battery, go through the inverter. Then there will be a second conversion in there, another 2%, 3% loss, power loss. So you can end up with 94 watt hour at the end of the conversion. And that 94, 95, something like that will be what is fed into the appliances. And that's the power loss from 100 watt hour on the left to 94 watt hour on the right. So this is probably the most efficient way to store energy. So, but let's compare it to the AC couple system. Okay, here we have the same solar array. We have an inverter, DC to AC inverter, and we also have wiring. That could be anything from disconnect, wiring themselves, breakers, appliances, anything like that. And then at the bottom we have the AC couple battery, which has a built-in inverter. So it receives AC and puts out AC, and in the top we have the appliances. Here we have the same 100 watts an hour output from the solar array that it gets converted to AC by the inverter. So we lose some of the power from going to DC to AC. So it comes out as 95 watts. The appliances, all the appliances can use it. Then when that power goes into the battery, there is another conversion from AC to DC, and we lose some power in there, probably another 5%. So we're down to 90 watts an hour by the time the power gets storage in the cell. When that power needs to be used, it needs to come out of the cell, converted to AC, and in there we're going to lose some power. We lose another 5% or so, 4 or 5%. So from DC to AC and goes into the wiring. It can be used by all the appliances. Now this number from 100 watts an hour to 85 watts an hour can change. It changes from manufacturer to manufacturer depending on the components, how tightly integrated it is between this DC to DC converter, the batteries to the inverter, the materials used. So that number will change from one manufacturer to another and from occasion to occasion. Some of the common uses for batteries nowadays is not just backup. For example, having a backup system allows you to use the solar PV when the grid is down. So most solar systems, or all solar systems without battery backup, need to stop producing power so power doesn't flow backwards into the grid and cause a problem for the linemen that are working on the electric grid. So the only way to have power when the sun is shining, if the grid is down, is by having a backup battery. Another common use is to power essential appliances during a blackout, so power outages. So refrigerators, freezers, pumps, medical equipment, anything like that needs to have power all the time. That would be implemented via a sub panel, or it could be implemented with a smart loads panel. Or if you have a battery that is big enough, a system that is big enough, you may be able to provide power to the whole home. So whole home backup system. Another use is to store energy for later use or self-consumption. Basically, in the 5 hours that the sun produces energy, it would absorb all the electricity or create all the electricity that you will need in one whole day, and then the cycle goes up again. That's another way to use all this solar energy. Another way to use batteries is without solar. You could take in all the energy that you need when the rates are the lowest cost, and then use the energy from the battery when the energy is more costly to you. So it's called load shifting or time of use. And lastly, living off grid is one of the uses for batteries. And if you have a big enough array and a big enough battery, you can probably live off the grid. Let's talk about solar batteries versus standalone batteries. Solar batteries are connected or installed in conjunction with the solar PV system. Until 2022, the IRS only allowed 30% federal income tax credit for batteries if these were charged by a renewable energy source, solar, wind, hydropower, something like that. So that's how the people could claim that 30% credit on the cost of the battery. Starting in this year, 2023, batteries don't have to have a solar array or a renewable energy source. They can be installed by themselves, and still you can claim the 30% tax credit as long as the battery is 3 kilowatts or higher or bigger for homes, or 5 kilowatts for businesses. Let's talk about the different ways to use the batteries, and here's a graphical representation of it. The first one, backup power, simple. Now in this drawing I'm showing a gateway here in the center of the screen, and the connectivity is a single line, but in reality this equipment connects to everything, connects to the grid, connects to the inverter, connects to the battery, and lastly connects to the home. But for simplicity, I'm just putting it in one connection in one side, just to show the flow of energy. And in the top right, having a clock or showing the time of the day, and right now it's about 2:30, 2:15 in the morning. Assuming the battery is fully charged, 2:30 in the morning, everything is working good. At that time, the electric grid is supplying power to the home. In the morning, the sun comes up. The angle of the sun is not good to produce electricity, so it's barely producing any kind of power. The sun is shining, but there's hardly any production. When it hits around 10 in the morning, the solar panels start producing most of the power. Peak production is coming up pretty soon. And at that point, because the battery is full, the energy is going to the grid and to the home, so it's forcing the meter to run backwards. By 3, 4 in the afternoon, the sun had moved away from the perfect angle, and even though there is light, there is just not enough energy production. So the grid start supplying power to the home, and still the battery is full, the panels are not producing any power. In the middle of the night, 11 or 12, in here, we're simulating a power outage, the grid fail. At that time, the gateway senses the problem and disconnects the home from the grid, and that's when the storage system is sending all the power, supplying all the electricity to the home. Again, that lasts all night long. In the morning, again, the sun comes up, but there is not enough energy production. At that time, around 10 in the morning, the sun is producing a lot of power, the panels are producing a lot of power, and it's not only charging the battery, it's also supplying power to the home. The grid is still down, and the battery gets charged a little bit, maybe full charge, and then at night the cycle continues. The batteries are providing power to the home. In the middle of the night, the following day, the grid comes back up. The gateway senses this and connects the home to the electric grid, and power from the grid is flowing to the home and to the battery until it is fully charged. Once the battery is fully charged, it's just the grid providing power. In solar self-consumption, which is another way to use the storage system, we basically avoid using grid power as much as possible. To do so, we'll store all solar generated power and use its energy throughout the day. Keep in mind that solar production is about 5 hours in Texas, so the system needs to generate all the energy used in a typical day during these 5 hours of peak sun radiation. Let's see how it works. Here is about 2:30 in the morning. The batteries are providing power to the home. In the morning, the sun comes up, but the angle is not great for solar production. At about 10 in the morning, the solar array is really producing power. In the middle of the day, lots of power is produced and the batteries are being charged. At about 3 or 4 in the afternoon, the sun has moved away from the ideal angle for solar production, and the batteries start supplementing power to the home. Then the sun goes down and the batteries take over, providing all the energy to the home. This continues throughout the night until the following day. We can see the process again. The storage system is providing all the power to the home. Then the sun comes up. At about 10 in the morning, the batteries are being recharged until about 3 or 4 in the afternoon when they start supplying power. And when the sun goes down, the batteries take over all the power supply to the home, and the cycle continues. The next day could be a cloudy day where there is little solar production. When the schedule calls for solar to supply energy to the home, one of two things can happen. Either the battery continues to be discharged, or the grid will provide power to the home and also recharge the batteries. This can be configured depending on customers' preferences. Some customers want to see the batteries completely drained out before taking power from the grid. Other customers prefer to keep a little reserve, which extends the life of the batteries, and it also can be used in case of grid failures. At night, the schedule calls for batteries to supply power to the home, and the cycle starts over. If the batteries were to be drained out during the middle of the night or at any time, then the grid will provide power to the home. Basically, we are consuming all the energy produced, and the grid is there in case that there is little solar production or there is extra energy consumption beyond what is stored in the batteries. Here we have another way to use the energy storage system, the ESS, and is to shift load to what is the most economical option for you. For example, from 10 at night to 6 in the morning, the price per kilowatt hour is 4 cents. So that would be the time when we want to charge the battery. And then the least time that we want to use the electric grid is from 6 in the morning to 9:30 in the morning, and from 5:30 in the afternoon to 10 o'clock at night, for example. And then in between we have 9:30 in the morning to around 5:30, which is 9 cents a kilowatt hour. That could be used in case the battery is down, but the intent again here is just to use as much as possible the 4 cents a kilowatt hour. In here the battery is halfway discharged and it is 3 in the morning. So let's see what that looks like. At 6 in the morning the new rate kicks in and only the battery is providing power to the home. The grid is disconnected or disabled. In this case, at 9:10 in the morning, the battery continues to provide power. We want to take advantage of that 4 cents a kilowatt hour. So we don't use grid power during the whole day. More importantly, around 5:30 and 6 in the afternoon, when it's the 18 cents a kilowatt hour, we continue to use battery power. At this point, the battery is almost completely depleted. 10 in the morning, 10 at night is when the battery is being charged again with the electric grid until it's completely full around 4, 5, and 6 in the morning. We can see it again running, filling up the battery, and then discharging during the whole day. And this is a way to use the storage system for the most economical way, for the cheapest electricity. Another way to do it is load shifting, but in this case adding solar panels. By adding a solar panel, you basically reduce the size of the battery if you want to, or if you want to have leave the battery size the same, you extend the life of the battery because you're not charging and discharging it all the time. So it's supplementing the power. So we see that around 6 in the morning, all this time from 10 o'clock at night to 6 in the morning, the grid is providing power and charging the battery. And at 6 in the morning, the battery is the only thing providing power to the home. At around 10 in the morning, the solar PV starts generating power, and it's enough power to charge the battery somewhat and provide electricity to the home. That continues until about 3 in the afternoon in a sunny day, and then at that point, again, the battery is sending all the power to the home to take advantage of that lowest rate possible, never using the 18 cents a kilowatt hour. And then at 10 o'clock at night, the cycles begin, it starts over, charging the batteries with electric grid in case that the solar PV didn't completely charge it, or it got discharged during the day, the rest of the day when solar wasn't producing all the power. We can see it again at night, charging the batteries. During the day, only the battery is producing power. Then solar kicks in, solar charges the battery. Then in the afternoon, solar is disconnected, the battery is doing all the work, carrying the home, and then at 10 o'clock at night, we use the grid power to charge the battery. Now, let's talk about the most common ESS products that are out there in North America, from established and newcomers, different technologies, different chemistries. Tesla Powerwall, 13.5 kilowatt hour, AC couple, LG Chem Resu 10H, 9.8 kilowatt hours, DC couple, M-Phase IQ10, 10.8 kilowatt hour. Sonnencore is a German manufacturer, established, been around for at least 10 years. Their system 10 kilowatt hour AC couple. And then in the bottom here we have some of the newcomers. Generac Power Cell, 9 to 18 kilowatt hours, DC or AC couple. Solar Edge battery, home battery, 9.7 kilowatt hour, DC couple. Franklin Whole Home, 13.6 kilowatt hour, AC couple. And Home Grid Stack, 9.6 to 38.4 kilowatt hours, DC couple. These are reputable North American market vendors that are more commonly used in the US. Now let's talk about something that not a whole lot of people talk about, and I think is one of the most important items on energy storage systems, and that is the chemistry used, because the chemistry dictates how long the battery is going to last, how much you can use it, what environments, temperature-wise, you can use it, number of cycles, and of course safety, how safe one compared to another. Let's talk about this. Nickel, manganese, cobalt batteries versus lithium iron phosphate batteries. Okay, so first, the thermal runaway is basically at what temperature the cells in the battery will actually initiate a fire. So what temperature runaway in the nickel, manganese, cobalt, and NMC is about 410 degrees Fahrenheit. Lithium iron phosphate is 518. So there's 100 plus degrees of temperature variation in there that the LFP can take a lot more heat before initiating a thermal runaway. So to me, that's a winner on that aspect. As far as cycles, the nickel, manganese, cobalt, a well-manufactured cell will last between 1,000 and 2,000 cycles. Cycles meaning charge, discharge cycles. While in the same conditions, a well-manufactured, reputable manufactured LFP batteries or LFP cells may last between 2,000 to 3,000 cycles, and I have seen that number as high as 6,000 cycles. So yes, it can last almost double the amount of charge cycles, the LFP. So to me, that's a clear winner on that category. Now, energy density, how many watt hour can you store per pound or per volume? In this case, it's per pound. In the NMC batteries, 68 to 99, depending on the manufacturer, depending on the balance of nickel, manganese, cobalt, and graphite and other materials. So 68 to 99 watts per pound, while the LFP is significantly less, so 40 to 54 watts per pound. So yes, this is a clear winner for the NMC, and that's probably why this battery is used for vehicles, for cars, where you want to have the least amount of weight and the least amount of air volume used in the vehicle, so you can transport it so needed. Perfect scenario for an NMC battery, which is transportation. But for a system that is stationary, it's not going to move, weight is not an issue, and volume in most cases is not an issue. I don't think it's as important to have higher density. You can get away with the lower density of the LFP. So let's talk about cobalt. It's mostly mined in the Democratic Republic of Congo, China, and Russia. 90% of the cobalt in worldwide supply comes from these three countries, which really have questionable labor laws, probably poor track on human rights and child labor, and all sorts of other ethical concerns. So right there is one important point that we need to consider when we use batteries with cobalt. Additionally, the presence of cobalt in battery cells also lowers the temperature threshold for a thermal runaway event, making it more likely to occur. And lastly, but not least, cobalt is in high demand, and is because of the scarcity, is making it more costly. So high cost of manufacturing will go into a cell or a battery cell that is using cobalt than if it didn't. So just giving those 3 points, ethical concern, thermal runaway, and high cost, puts the LFP batteries, which are not using cobalt, ahead of the NMC batteries. In my opinion, that's a clear winner. So let's separate the 8 manufacturers and products that we saw a minute ago based on their technology and how well they're established in the market or not. So in the nickel manganese cobalt technology, of course, we have Tesla with their Powerwall, and we have LG Chem with their Resu H10 product. As far as LFP, we have well-established vendor Enphase IQ10 and the Enphase IQ3 and all the products they have. It's a smaller battery, smaller storage. And also we have the Sonet Core 10 kilowatt hour AC couple, well established, one of the best products in the market today, probably as good as Tesla Powerwall, using LFP batteries, LFP cells. As far as the newcomers to the market, we had Generac Power Cell. They bought a company in 2019, I believe. So they entered this market. These are the company that had provided generators as a backup solution, backup energy solution for the better part of 20, 30 years. And now they're entering in the battery storage unit. Another newcomer, Solar Edge, also they partnered with a Korean manufacturer probably 2-3 years ago. And their product uses nickel manganese cobalt cells, 9.7 kilowatt hours DC couple. Another newcomer, the Franklin Whole Home battery cell. Here is only showing the battery module that it comes with the gateway. So it could be it's an AC couple at 13.6 kilowatt hour using LFP cells. I really like that product, and we'll see why in the next video. In the next video, I'm going to do a detailed review comparison of all these products side by side. And the last one that I'm going to list on this list is the Home Grid Stacked, also using LFP, also a new market player with their DC couple batteries from 9.6 to 38.4 kilowatt hour. And that's all for an introduction to storage systems, energy storage systems. We're gonna have another video where we explain, compare at least 8 of the most popular North America vendors, very popular, and using both NMC batteries and LFP batteries and pros and cons between them. Watch that video. Hope you like it.